Hi everybody. So I want to record a lecture today on projectile motion, and I will set up the kinematic equations for the case of projectile motion, and then we'll do an example where a projectile is launched horizontally. So first let's just begin with the kinematic equations. We've learned about the kinematic equations in vector form. They are, in general, so these are valid in the situation where a vector is equal to a constant, right? So that's the first equation. A is a constant. And then we've got the formula for the velocity. V is equal to v0 vector plus at. And then we've got a formula for the position vector. R is r0 plus v0 vector times t plus 1/2 at squared. And what you have to remember is that each of these is really shorthand for three different equations. And for projectile motion, we don't really care about the z direction. We're just going to assume that the entire motion is in the xy plane. So we can always reorient our axes so that the motion is in the xy plane. And so the basic picture is going to look like this. We've got a vertical direction and then a horizontal direction, x and y. And, in general, for projectile motion, you have some kind of parabolic path. And so it's going to look something like this. And we're just going to orient our x-axis so that our x and y axes so that y is the vertical direction and x is oriented in the same direction as the horizontal motion of the projectile. So the thing to keep in mind about projectile motion is that the acceleration for a projectile always points down, and it always has the same magnitude. So all of these vectors that I'm drawing here are the same length, okay? And so the acceleration at all times while this projectile is in the air is always minus g, okay? And so A we can write as minus g y hat. So the equations in these various directions will simplify. So A x is 0, ay is equal to minus g, vx is equal to vx0, and then there would be a plus a sub x times t, but remember that's 0. And then vy is vy0 plus a sub yt, but a sub y is equal to minus g, so this becomes a minus g times t. And then we have the position equations. So x of t is equal to x0 plus v0 x times t plus, and then again there's a 1/2 a sub x t squared here normally, but this is 0 for projectile motion. And then finally there's y is equal to y0 plus v0 yt minus 1/2 gt squared, because a sub y is equal to minus g. So these are our kinematic equations, okay? So let's put a box around these. These are important. We're going to come back to those. Let's apply these to a particular example where we have a horizontal projectile. So this is sort of like a classic example that we call the Thelma and Louise example. So you imagine that there is a cliff, and Thelma and Louise are driving in a car, and they're moving along, and then they drive right off the cliff. And their initial velocity as they go off the cliff, v0, is equal to 30 meters per second, let's say. and in the x-hat direction. So we'll put a vector sign over that velocity vector. And we'll say that the cliff has a height, y0, that's going to be their initial height, of 1,000 meters. Okay, so we'll assume this is 1,000 meters. Okay, so that's the initial height that they start at. And I'll also assume that the edge of the cliff here is at x equals 0. Okay, so this point here is at x equals 0. So what's going to happen, they're going to follow a parabolic path and they'll land somewhere here. And what we want to know is what their final position is. Okay, their initial position is 0. So we'll say x0 is equal to 0 for simplicity. We can always choose our coordinate system so that that's the case. Okay, cool. So let's now think about a bunch of questions that we might want to answer. So the first question is, how long are they in the air? Okay, so what is T final minus T initial? T initial I'll just assume is 0. So I'll assume T equals 0 corresponds to this point where they're just leaving the cliff. Okay, so what is T final? B. How far do they travel horizontally? So what is x final, right? C. What is their speed when they hit the ground? What is their final speed? So v final is the magnitude of the final velocity vector. So I'll have to calculate what my final velocity vector is before I can take its magnitude to calculate the speed. And then finally, can I come up with a formula for the trajectory? And by trajectory, I mean a formula for y versus x. Not y versus t or x versus t, but rather y versus x. So let's deal with each of these questions one by one. So part A, okay, how long are they in the air? So which of these kinematic formulas do you think we should use in order to determine how long Thelma and Louise are in the air? So pause the video for a moment and take a minute to figure that out. Okay, so you've thought about it for a little bit, and hopefully you arrived at the conclusion that this y of t equation is really the one to use. And so let's figure out how to use it. So y of t is equal to y0 plus v0 yt minus 1/2 gt squared. What do we know and what do we not know here? We know y at the final time, if I evaluate this at tf, so I'll change all these to f's. So at tf, y final is equal to 0 because that's where they hit the ground. I know y0 is 1,000 meters, so I know what that quantity is. I'm not going to plug it in until the end. And I know v0y is 0 because their initial velocity is purely horizontal. There's no y component to the initial velocity. And so this whole term vanishes. And so really what I have is y0. If I move this minus 1/2 gtf squared to the other side, I have y0 equals 1/2 gt sub f squared. And I can solve this for t sub f. T sub f is then going to be equal to the square root of 2y0 over g. So that's the formula. And now we can plug in some numbers. T sub f is equal to square root 2 times 1,000 meters divided by 10 meters per second squared. And you see that the units are going to work out. And so this number ends up being about 14 seconds. Okay. Great. So we know we know how long they're in the air. Part B. What is the range? How far do they travel horizontally, right? So what is delta x, which is defined as xf minus x initial, but in this case, this is 0. So what is x sub f? So I know, I know x as a function of time. So x is equal to x0 plus v0x times t. And this is what I just said was 0. This is the same as x initial. So this is 0. And if I evaluate this at tf, then I get xf there. And so this tells me that x sub f is equal to v0x, which was 30 meters per second, times t sub f, which was 14 seconds. Okay, so this is equal to 300, so this is 420 meters. Okay. Okay, part C, moving right along. What is the final speed? So let's think carefully about what we have here. So notice in my picture that right before they hit the ground, the instant before they hit the ground, that's what we want. We want to know what the final speed is. Well, I know that the velocity vector is going to point down and to the right, right? So the length of this vector is what we want. We want VF, which is the length of that vector. And I know that it's got a horizontal component, VF sub x, and it's got a vertical component that points down, VF sub y. And I need to figure out what each of these are before I can use the Pythagorean theorem in order to calculate the length. So obviously the equations to use are the equations that tell us what the velocity is as a function of time. So I know Vx is equal to V0x for all time, right? Because the acceleration in the x direction is 0. So that one was easy. So this is just 30 meters per second. I know Vy is equal to V0y minus gt. Well, V0y was 0 because the initial velocity is purely horizontal. And so I know gt as well. And I could go ahead and evaluate this at the final time. But let's go ahead and keep this in terms of formulas for a minute. So V is equal then to, V vector is equal to V0x x hat minus gt y hat. Okay, so this is this velocity vector, and so far I've kept it, I haven't evaluated it at any particular time, so this formula is valid at all times while they're in the air. Its horizontal piece is not changing in time, and the vertical piece is increasing. So now let's evaluate this at the final time. So VF final vector is V0x x hat minus g t sub f y hat. And so now if I want the magnitude, VF, which we can just write without the vector symbol, that's square root V0x squared plus minus gt quantity squared. So this minus sign is going to get squared and is going to go away. Notice that this gets longer and longer as time increases because this vertical piece, which starts off at 0, the vertical component of the velocity begins as 0, is increasing as time goes on. And so if I plug in some numbers, I have V sub f is equal to square root 30 squared in meters per second plus minus 10 times TF, which is 14 seconds, right? And I was a little bit loosey-goosey with the units here. The units here for the 30 are meters per second, and that gets squared. And then here I have meters per second squared times seconds, so that's also going to be meters per second, which is going to get squared. But then there's a square root over everything, so the final units will be meters per second, so that's good. So, so this is, let's see, 30 squared plus 140 squared, which is going to be coming out to approximately 143 meters per second. Cool. Okay, so we're almost done. Part D. What is y versus x? So this is called the trajectory when you eliminate the time and you just describe what the path of the projectile is through the air. So I know y of t and x of t, and so the idea is to solve one of those for t and then plug it in. So y of t is equal to y0 plus v0y times t minus 1/2 gt squared. But v0y was 0, so I can get rid of that. And now I want x of t was equal to x0 plus v0x times t. And x of 0 I defined to be 0. I just chose my origin to be at x0 equals 0. So now I can solve this equation for t. T is just going to be x divided by v0x. And then I can plug this into this equation. So I get y equals y0 minus 1/2 g times x over v0x quantity squared. So this is just y equals y0 minus g x squared divided by 2v0x squared. And notice that this is also a parabola, right? This is a parabola because it goes as x squared and it's concave down because this minus sign, right? So this is exactly this parabola that we were drawing before, y versus x. Great, so I hope that this was helpful to you, and if you have any questions, you can always send me an email. Thanks for watching.